Any questions about last time, maybe? Yes.
In the book, wait, I don't have it here, but in the book, at one point, at the end of chapter 4, they considered C to be 1, right?
Yes.
I was wondering the consequences on the exercises where we consider C as being C. Like, do we have to?
Well, that's a choice that we have to make with ourselves. Are we going to use the convention that C is equal to 1? We don't have to. But the reason that C is not equal to 1 is just because of our particular choice of unit systems. The fact that historically we chose this amount of distance to be 1 in some unit system, a meter, and this amount of time we also call 1 second. Having chosen those particular sets of unit systems gave us back C as this ridiculously large number. But you could have also just picked some other unit for length and for time in such a way that C happened to come out exactly as 1. Now this is what the book does at some point. It just says, well, from now on C is going to be 1. We have to make a choice if we want to do it as well. And I prefer to do so. This is why I constantly forget C's because in my mind they're 1, so I don't have to write them down. This also when we did this exercise 1 week ago, that I said, wait, this is going faster than light. And then you said, no, it's not faster than light. That's because in my mind, light is 1. And the number was, I don't forget what it was, 1.5. As, oh, that's faster than light. Yes, it's faster than light if light has the value 1. It's not faster than light if light has the value 3.0 times 10 to the power 8. So I constantly get confused with the units because I consistently use C as 1 units. I'm very happy to keep the C's in. And that might be the most logical choice in regard that it's much easier to have your formulas while the C's still in there and then set them back to 1 than the other way around. So it's just a choice. So I propose to keep the C's in. That will require you to check my formulas every now and then because I tend to forget these things. So let's keep them in for now. And if you want to make the connection, because I think that's your question, back to the book, just take my formulas and set C equal to 1, you will get the formulas of the book back. Any more? No? Alright. So, any key concepts of last time that we might want to use this time? Can you take a guess? Well, that is the most important one because that is the one, of course, from which we have to write everything. So see this as a sort of summary of last time, a very short version. What we did was we took this as our postulate. We called this number that comes out C squared d tau squared. And this is not the physics, this is the physics. We said it was invariant. That it's the same number regardless of what inertial system you are in. That was our basic starting point. And using this basic starting point, because we keep it up here for future reference, given this basic starting point, we derived all kinds of things. We derived that d tau is the proper time. In other words, time between two events as measured by a person sees two events at the same position. We also derived from this the time dilation formula, this one. We also derived in 2 separate ways during the tutorial B that there is something called Lorentz contraction. That was this formula. What we got back from this was also the Lorentz transforms. Gamma d tau minus v over c squared dx. This is one of these moments that I ask you to check my C's, but I think they're correct right now. The Lorentz transforms derived all this stuff. What else? I think this is the most important stuff that we saw last time, right? And the only thing that we used was this expression being invariant. That's all that we put in there. There was a second postulate for relativity. This is one of them. And there was one that we haven't really used so far. Do you remember what that was?
Laws of physics are the same in all initial reference frames.
Exactly. So this is one postulate, and apparently this postulate is enough to give you all kinds of interesting effects, can all do all these exercises. And there was this other postulate, which you call the principle of relativity, that the laws of physics should be the same in all observer systems. It's called the principle of relativity. We haven't really used that yet, but it will become extremely important later on. Principle of relativity. Now, just to be sure, the principle of relativity does not say that the laws of physics will give you the same numbers in every frame. Right? There's many examples of numbers that are different from one frame to the next. That's not the statement. Of course, numbers are going to be different. That was already the case in Newton's laws of physics. No, what's going to be the same is the rules that these numbers obey. That's going to be different. That's going to be the same in all inertial systems. So these two really summarize everything that we have done last week. Now today we're going to do 2 steps. One of them is we're going to use this one more time, but now in a different notation. So no new physics, just different notation, and that notation is going to be very important for general relativity. And then in the second half, what I would like to do is show you how acceleration comes into the picture. Because up to this point, all of this only holds for people in inertial systems. So both the principles, as we have used them up till now, only hold, or only have been assumed to hold, for inertial systems. Is there anyone who can tell me what an inertial system is? If not, then we're going to spend some time on this because it is of paramount importance. Yes?
There's no acceleration.
With respect to what?
To yourself.
Every time that I'm in any system, I will have no acceleration with respect to myself. I will not even have velocity with respect to myself. In my own system, sorry?
But you can feel the acceleration.
Okay, as in your tummy or something like that, when you're being pushed back when your roller coaster goes downhill. Yeah, exactly. Well, it's not wrong, but I want to have. We cannot build physics upon the statement whether you feel something in your tummy or not.
No, okay, but you can have like more precise apparatus.
Yes, of course. Well, that's what we're going to do. So you're saying if you don't have a feeling in your tummy, then that means you're in an inertial system. Yeah. Okay. Well, I mean loosely speaking.
Yeah.
Yes. Well, that's correct. No, it's correct. But of course, we have to put it on more mathematical footing, I guess. Paulus, did you have an?
You said something about Newton's first law.
Yes, that is the one. That is, by the way, just his statement, but more mathematically put. As a sort of rule of thumb, you can say, well, if you're not in an accelerating system, then you are in an inertial system. But that's sort of a shaky statement because you have to accelerate with respect to something else, right? And saying, well, I'm not an accelerating system without saying with respect to what you are or are not accelerating makes it a very empty statement. So we have to have something else, some objective meaning, some objective rule that tells you if you are in an inertial system or not, without having to look at other systems to compare yourself with. Something that you can do within your own observer frame without having to revert to other systems. Oh, well, look, that one is accelerating, so therefore I am not, or something like that. Something that you can tell without looking at other systems. That's what we're looking for. Yes, the answer is
If you
Newton's first law.
If things fall in a straight line, then you know it's accelerating.
Well, there we go. There you go. And again, what you're saying now is an application of Newton's first law. And I think that I had to be reminded by you, the electrodynamics people who did the previous course. I also made this statement that if you want to know if you are in an inertial system, I think I used stroopwafels on a train. Okay, stroopwafels in physics, why not? If you want to know if you are on a train and whether the train is accelerating, well, you can look out the window and say it's accelerating with respect to the Earth, yes? But then again, it just means that you have a relative acceleration. Maybe the train is standing still and the Earth is accelerating backwards. So that really doesn't work. But you can tell whether you are accelerating or the Earth is. The only thing you have to do is take a stroopwafel, or any object really, and you throw it upward. Then Newton's first law states that things want to go in a straight line with a constant velocity. Yes? This is exactly Newton's first law if there's no forces acting on the thing. Now in this case there is a force acting on the thing, the stroopwafel that I'm going to throw up, because there's a gravitational force. Okay? Forget about that one. I'm talking about, do you have a horizontal acceleration? That's what we're looking for. Now if you find that the stroopwafel is landing to the back of you, then that means apparently that you have gone faster than the stroopwafel. Agreed? So that means that the train on which you were standing was going faster than the stroopwafel was. Then again, if you throw the stroopwafel upward and it will fall down next to you, then you know that you're not an accelerating frame. You might be in a moving frame though. This is Newton's first law. If you throw something upward and it feels no force in horizontal direction, it will go with the same horizontal direction as did at the moment when it left your hand. Right? If it was already going with 120 kilometers per hour in horizontal direction, it will still go with 120 kilometers per hour, but then again you are too. So that means that it will drop down exactly next to you. So you cannot do the stroopwafel trick to find out if you are moving, but you can use it to see if it's accelerating. The thing lands to the back of you, then you see, wait a minute, according to Newton's first law, it should have gone along with me and landed next to me. If it didn't, if you find that Newton's first law does not hold in your experiment, you know exactly that you are not an inertial frame, that you are standing on something that is accelerating. Notice that you don't need to look out the window to look at something else with respect to you are or are not accelerating. You just need a stroopwafel. Okay? Or some mass, anything. So Newton's first law tells you if you are in an inertial system, so we can use that actually as a definition of an inertial system. Inertial system is a system in which Newton's first law holds. And I'll stress this one more time. You do not need to look at other systems to compare yourself with in order to find out if you are accelerating or not. You just need a stroopwafel. System in which Newton's first law holds. This is a highly non-trivial statement. Yes?
Can you give an example of a case where Newton's first law doesn't hold?
Yeah, of course. Suppose that you're, say, an American president, you want to send rockets to Syria or something like that. Okay? This is an example. The thing is flying towards Syria. The Earth is not an inertial system because it rotates around itself and it goes around the sun. Now, let's focus on the rotating around its own axis. You will find that the rocket will not land at exactly the point that it would have if it was not spinning around this axis. And in fact, these people who send rockets, but also just people who fly planes and such, they have to keep this effect in mind when they calculate how they should go from A to B. And in fact, it's going to be important in the second half because there's this thing called fictitious forces that you have to deal with. But this is the idea. Here's an example of how you can find. If you send a rocket to Syria, you've done a calculation using Newton's laws, and you find that it does not land in Syria, and it's not a mechanical issue or whatsoever. Yeah, it's okay. It's a macabre example. Maybe I should have used something else. But in all seriousness, if you throw something through the air, and it does not follow Newton's laws, then you know immediately this is not an inertial system. So Newton's laws is ridiculously important in relativity. It tells you if you are allowed to use these rules. And everything that we've done only is true at the moment that you are in a system in which Newton's first laws hold. If not, you have to do something else. And this, of course, is where general relativity comes in. What if you're not in an inertial system? Now, one statement about inertial systems, one more. That is, if you are in an inertial system, and suppose that some other guy is moving with constant velocity with respect to you, but you already know, you've done your stroopwafel trick, you already know that you are in an inertial system. Is then the other guy as well, if he's moving with constant velocity? I see you nodding. Somebody who's shaking his head. Some people who don't know. So here's the question again. Suppose you've done the stroopwafel trick, you know you are in an inertial system. And some other guy comes along and he's moving with constant velocity with respect to you. Is he also in an inertial system? Now suppose that this guy has no stroopwafel, he cannot tell by throwing stroopwafels around. He has no tummy, so he doesn't feel the... Well, but this, by the way, is a tummy feeling, yes? the tummy is your stroopwafel in that sense. Your tummy wants to stay back while you're moving forward. This is why you feel it in your stomach. No, really. So you can use your tummy as an inertial system, but you have to be careful, because if you've eaten something bad, then you might still be an inertial system, and that's the reason why you feel bad. But it's the same idea. Your tummy wanting to stay back is the same thing as the stroopwafel. So the guy in the other system does not have a tummy or a stroopwafel. How do you know? How does this guy know whether he is in an inertial system or not? He has only you to look at, and you know that you are.
You can also see that you are in an accelerating frame, right? You can see that.
Yes, but there's no acceleration in my question.
Oh, sure.
Because there's one guy, he's in an inertial system, and the other guy is moving with constant velocity with respect to you. Question, is he in an inertial system if you know that I am? The answer is yes, by the way. Now, don't take this as a statement from me. Should we just prove that here and now? Wasn't part of my original plan. We can do it just here and now. So my statement is, if you are an inertial system, and you see somebody moving in some other system with constant velocity with respect to you, then he is also in an inertial system. So let's prove that. So we have that fully complete. Claim. If we did it with primed and unprimed. When I say unprimed observer, do you know what I mean by this? It just means one person whose coordinates we're going to write with primes, without primes. If unprimed observer knows by the tummy trick that he is in an inertial system, then any primed observer, and let's make it more specific, that guy must move with a constant velocity with respect to the unprimed. WRT stands for with respect to. If unprimed observer is an inertial system, then the primed observer, moving with constant velocity with respect to unprimed, is also in an inertial system. Different inertial system, still an inertial system. This is the claim. The claim is true. The question is how to prove it. Suggestions. What is the key thing that you need to find out if you are in an inertial system? Don't say stroopwafel or tummy. It's
You need to know if you're accelerating.
Sorry?
You need to know if you're accelerating.
Well, yes, that's just a rephrasing of the question. How do you find out?
Newton's first law.
Newton's first law. All right. Just find out for yourself if then the other guy sees Newton's first law being upheld. If so, answer is yes. That's the only thing you have to do.
But
So
if
let's
the
find
other
out.
guy doesn't have a stroopwafel or something, then how do they test
Well,
it?
that is very true. So,
So like, I thought that was the part of the proof we would do it without him having his own.
well, my proof is more mathematical in nature. That the guy doesn't have to have one in order to find out.
Okay.
But you're right. I mean, if he wants to actually check that that is the case, he still has to throw some rocks around or some stroopwafels or something like that. Here's the proof. Let's go for the first guy. So let's stick with the cookie, okay? He throws a stroopwafel around. How would you write that this is the position of the stroopwafel? X as a function of t. How would you write down Newton's first law in stroopwafel terms? In this position of the stroopwafel terms. What does it mean when I say something obeys Newton's first law?
Equals v times t.
Actually, that is a very nice one. Yes, I wasn't going for that one, but sure. And then this v is constant, yes?
Yes.
Okay. And let's put some primes there for in a moment. In a moment, we're also going to look at t primed, say. That's for the other guy. All right, well, I agree with this. And this v has to be constant, because this is Newton's first law. Things will go with a constant velocity. All right? Okay, let's take two derivatives of this. Why? Because. What's the second derivative of the stroopwafel's position as a function of time. If you know that v is a constant.
0.
It's 0. It just says no acceleration for stroopwafel, as seen by this guy. What we're going to do now is look at the same stroopwafel as seen by the guy in the other system and prove that for that other guy this is also true. Because then you've shown that the stroopwafel will have no acceleration for either of the two, so both of them are in a inertial frame. Parse that for a second so you understand why this is a good translation of the question. Newton's first law says stroopwafels, when left alone, should have a constant velocity or no acceleration. You know that this is the case because that's part of the premise of our question. Now the question is, look at the same stroopwafel from the other guy's perspective and see if it still does not have any acceleration. If so, Newton's law is obeyed in both systems and both of them are in an inertial frame. That's how we're going to do this. Question, how do I write the position of the stroopwafel as seen by the other guy as a function of time? Prime means the other guy in the other frame. It's not a difficult question.
It's the same v and t prime.
It's not the same v.
It's relativistically summed v or not?
Not relativistically. This is all in Newton.
Okay.
Still, we're just doing Newton's mechanics. You can also do it, by the way, for relativistic, but let's do it for Newton first. But this is the right direction. If I see something fly around with 10 meters per second, yes? And you're moving with 5 meters with respect to me, what is the velocity of that thing in the other guy's coordinate system?
V plus v prime.
Yes. You would say something like this. Let's put an S here for stroopwafel, STR. Okay? That's the velocity of the stroopwafel. But there's also relative velocity between the two observers. Let's call that one V. Okay? Do you agree with this? That the stroopwafel will go a little bit faster in the other guy's frame because it will go with its own 10 meters per second plus the 5 that the two observers are moving with respect to each other. I see 2 questions. Yes.
Can we also use, like, to be more correct, additional rule?
Yes, this is what Nelson. But we can use that too. Yeah. But let's do that in a second. I'm going to leave it like this.
Okay.
But sure, we can put this in a second. Was it your question too?
No.
Okay.
So the v is the velocity of your prime observer, right?
With
The
respect to the
other
first
one.
guy, yes.
Yes. No, never mind.
Okay.
My question is solved.
All right. Could also be a minus. Depends on if the other observer is moving toward the stroopwafel or away from the stroopwafel. Okay. If he's moving toward the stroopwafel, there's a plus because he sees the stroopwafel coming towards him with 10 meters per second, and he himself is moving 5 meters per second. So the relative velocity within the stroopwafel, you see the thing move much faster towards him. That's 15. But if the stroopwafel is coming towards him, he's walking away with 5 meters per second. Then it takes a little bit longer for the stroopwafel to catch up with him. You're going to have 10 minus 5. So there is a plus-minus issue, but it's beside our point. So here's that thing. At this moment you might say, but wait, didn't we derive that the relative velocity now, I mean that the adding of velocities goes by a much more difficult rule in special relativity? Okay. In that case, this is going to be replaced by 1 plus or minus u, we called it u before, now it's called v stroopwafel, times v over c squared. Does not change my argument. Do you agree with this so far? Stroopwafel as seen from one frame, now seen from the other guy's frame?
Should the t be primed?
This should be a primed t. I agree with that. Yes. So how's the t primed? How's that? Looks a little bit different than the other guy's t, right? There might be a gamma in there somewhere.
Like it could look different, so
Yes.
that's why it's primed.
No, you're right. That's very true. No, that's very true. Will not change my argument. But you're right. I mean, if I started Newtonian, then I said, you know what? Let's do relativistic. Add this because we derived this. And then you're right that this should not. We're going to do this relativistically. Then this t should not be that t. They're different t's. So let's call them primed. All right. There we go. Now, so this is how fast the strobe waffle is moving in the other guy's observer frame. My claim is that the second derivative of this thing, the velocity as seen by the other guy, is also going to be 0. In other words, that Newton's first law is also true for the other guy. Is that obvious to you? Second derivative is still going to be 0? So we're going to take the second derivative of dx. By the way, derivative with respect to t or t primed?
Prime.
It's primed, because you're going to look at how the strobe is moving in your frame using your watch. That's t primed. Two derivatives of this thing with respect to t.
0.
It's 0. Because this whole damn thing is constant, isn't it? Because the stroobwafel's velocity was already constant. The v between the two observers is constant. All of this is constant, is 0. Which is again Newton's first law. So this claim is true. Very important. Wasn't what I was going for today, but it is important for your understanding of inertial frames. It's very nice if you find yourself without a stroobwafel and you see me walking by with a stroobwafel and I am in an inertial frame, then you just look at me. If we're going with constant velocity with respect to each other, then you know without your stroobwafel that you're also in an inertial frame. Yes?
I don't know if it's a very good question, but on Earth, are we in an accelerating frame because we're rotating, or?
Yes.
Yeah.
Yes, we are. We are now not in an inertial frame. If I throw stroobwafels around, you will not find it because it's hardly detectable, especially with all the extra effects from the friction of air and such. This is why I used a somewhat macabre example of sending rockets to places. But if you go over large distances where this effect can build up, this is when you start seeing it. And one other example, it's somewhat messy this example, but it is nonetheless true. Clouds. They go in curved trajectories. This is not because of the wind blowing. There is some wind blowing. This is why I call this example messy. But they have a natural tendency to go into circular motions when they get close to the equator. This is because they're not in an inertial frame. If the Earth had been an inertial frame, no rotation, they would have gone in a straight line. They don't. And this is not because of the wind blowing. Yes?
But if the Earth is not in an inertial frame, when we feel it?
Yes, but the thing is, the faster the acceleration is with respect to an inertial frame, the larger the effect is. And the Earth is rotating, but not fast enough that you would actually pick up on that.
But is rotation accelerating as well?
For all practical purposes, the answer is no. The acceleration is not. The acceleration itself is not changing in time. It's a constant acceleration. I say for all practical purposes, in real life it is, because there is a certain amount of drag and there is a nutation of the Earth, so every now and then it doesn't just revolve around its axis, it also precesses and it also nutates. So that means the acceleration strictly is not constant itself. But those are really small effects. I mean, you have to go to ice ages to see their difference and such. Okay. But that means, going back to our original story, that everything that we've derived, all these things, and by the way, you're right, there should also be the velocity addition rule here. Let's use our original terminology again. We also derived this. All of this came from this, but this is all for inertial systems. So that means that all these rules we can only use if we ourselves are inertial systems. Now I made this point last week. The thing that you're looking at does not have to be in an inertial system. You are allowed to look at things that accelerate as long as you yourself stay in an inertial frame. You can throw a magnetic stroobwafel around and have some magnetic fields here and there, so it will accelerate in all kinds of directions. Then you say, wait a minute, that thing is not an inertial system. No, that's true. But you are. So you're still allowed to use these rules. Okay? That's a huge misunderstanding about special relativity, that you're only allowed to look at things that go with constant velocity. You're allowed to look at things that accelerate as long as you yourself don't. And having that made more strict now, as long as you yourself are in an inertial system. Well, so that's it. Now, again, wasn't what I was going for today, but it's good to have this on firm footing. You only need to find one person who is in an inertial frame, and then you know of all other people in the universe if they are as well. If they have a constant velocity with respect to that first guy, then all of them are in inertial frames, and all of them can use this. There's two ways that I can go now. I wanted to introduce the notation. That was my original plan for how I'm going to build up this lecture, but now we're already, head deep in our inertial frames. So I might as well make the step what happens if you're not in an inertial frame. How about we do that first, conceptually? Okay, and then I will reserve the notation that I wanted to introduce for the second part. Switching up with my original plan, but we're now talking about this anyway, so let's do this. Hey, what happens if you're not in an inertial frame? Well, that's the question, isn't it? Anyone dare to take a guess?
Newton's first law is no longer going to apply.
That is very true. So what does that mean if Newton's first law does not longer apply?
You will observe curved movement.
I would say accelerated movement, yes. That is true. If you find that Newton's first law in your frame does not apply anymore, if you're not in an inertial frame, then you know that it's a stupid example, I just keep on going back to it. Then let's stick with stroopwafels. Then you know that your stroopwafel will, in your frame, seem to accelerate. Right? Without any external cause. Of course stroopwafels can accelerate. Just magnetize them and throw them into a magnetic field, and we will accelerate the stroopwafels, even in an inertial frame. But if you find that the thing doesn't feel any forces whatsoever and it will still accelerate, a clear violation of Newton's first law, again, then you know that you're in a non-inertial frame, that you're in an accelerating frame. So this is what you will see happening. You'll see things all of a sudden accelerate without external causes. You're completely used to this effect, by the way. What I'd originally set up, but because I'm now switching the order of my lecture, I don't have the time to show you this picture, but I went to the Efteling yesterday. It's an amusement park. Went there yesterday, and I was in a roller coaster. This really sounds like I'm just making this story up so I can make the bridge to this. I actually went there. I have pictures to prove. Okay, this is why I wanted to. In the second half, I would have brought it up on the screen, and I still will. So keep that in mind. I was in a couple of roller coasters yesterday, and indeed I felt that things were trying to stay backward. I didn't bring any stroopwafels, but I did feel my tummy who wanted to stay backward. It was accelerating backward, and this is what I felt, of course. Right? There's one of these rides that they have where they just give you a 98-degree drop downward. It's a new thing. It's called the Baron. Yeah, the balloon. I mean, I hated the thing. I was with my girlfriend, and it so happened that we were allowed to sit for a second ride. I got off, and she stayed for a second ride. Braver than I am, apparently, because it's really steep. Anyway, you can feel, this is your effect, you can feel that you're in an accelerated frame, okay? We're going to assume that the Earth is, for our practical purposes, an inertial frame from this moment on. It isn't, but suppose that it is. I could tell that I wasn't anymore. But wouldn't that mean that objects, if I would left them in my hand, would have maybe tried to stay behind? That's the whole idea, isn't it? But isn't it almost as if there is something pulling on my stroopwafel because it's staying behind? In my inertia, in my frame, I have an X direction and I have a Y direction and a Z direction sticking out from me. In that frame, things will accelerate backward, don't they? And you're used in Newton's laws that things only accelerate at the moment that you feel a force. Force is the cause of acceleration. Now in this case, I see something in my frame. I'm falling downward in that ride, enormously high acceleration, 9.81 meter per second squared or so. I saw that stuff, again in my frame, in my observer frame, was accelerating upward. Now you would say, no, it's you who's accelerating downward, and that thing has just Newton's first law, wants to stay behind. That's true. But suppose that I wasn't able to see all of that. I didn't see the rest of the Efteling. I didn't see that I was the accelerating person. Then I see stuff accelerating upward. And from my Newton's theory, I know that things only accelerate when they feel a force. So I would conclude, wait, there's a force acting on me, or on the stroopwafel. Some force is pulling the stroopwafel upward. Again, from the sideline, you know, no, it's you falling downward and the stroopwafel is just staying behind. But for me, it looks as if the stroopwafel is being accelerated upward. And Newton then tells me, well, that means apparently there's a force acting on your stroopwafel. Now, that force is not there. The only thing that the thing is experiencing is his tendency, Newton's first law, to stay behind. But to me, it looks like a force. Do you see that? This is called a fictitious force. That's an actual term in physics. Something that looks like a force because apparently to you things start accelerating, so there must have been a force. But the only reason that you see things accelerating is that you have decided to not stay in an inertial frame. So things tend to stay behind. There are no forces, there's just stuff that's trying to stay behind because of Newton's first law. But as seen by me, it looks as if there's a force acting on that thing.
What do you call it?
The fictitious force. In Dutch we call it schijnkracht. But anyway, fictitious force. Never heard of this?
No, haven't had that in high school. I think.
Okay. Well, this is because, well, you have actually, but your teacher probably never pointed it out as such. Because in high school and such, and when you learn Newton's laws, you typically only apply them in inertial frames, don't you? And your teacher probably never said that. But at the moment that you're not in an inertial frame, you're in an accelerating frame, that means that apparently all your particles start have accelerations without any forces. And again, that means that for people who are in that non-inertial frame, it looks like there are all kinds of new forces popping up. Now, these are called fictitious forces. They're called fictitious because they're not really there. It's just you having made the bad decision of trying to use Newton's laws in a non-inertial frame. So this is why they're fictitious. If you would have just stayed in your inertial frame, you wouldn't have seen these forces. But you could also say, well, you know what? They are not really fictitious because things are really accelerating. So there is something going on. Now, how do you call these things and whether they are real forces or not is just a matter of semantics. Okay? So let's write this down here because it's an extremely important step towards general relativity. If not in an inertial frame, these are just the steps that I just made in a second ago. If you're not in an inertial frame, objects will have accelerations without there being forces on them. Right? This is my stroopwafel staying behind where I and this right are falling downward in the right and the Efteling. Objects will accelerate without any forces. So, to a person in that non-inertial frame, it will look as if there is a force because he sees an acceleration. This is what I'm writing down right now. So for observers in this frame, it appears there are forces. And again, we know there are no forces. It's just stuff trying to stay behind because Newton's laws tell them to. And we call these fictitious forces. And the way that I always have this in mind as sort of conceptual ideas, fictitious forces are the forces you feel or you experience in your frame because you are dumb enough not to stay in an inertial frame. This, by the way, also gives you some recipe to determine whether a force that you see on your stroopwafel is an actual fictitious force or a real force. If you cannot find any frame in which that force disappears, it's a real force. Right? If you just go back to the original frame, some inertial frame, and the force is not there anymore, then you know, oh wait a minute, it wasn't a force in the first place. It was really just me being in the wrong frame. Now let's give a prime example of this. And this is something that everybody has heard, regardless or not your respective teachers ever used the word fictitious force or inertial frame. I will erase this. Okay. Here's the example. Example of fictitious force. Just in Newtonian mechanics, no relativity per se. Here it is. It's my intent to draw on the Earth. Okay. Here's the moon. What are the forces on the moon?
Gravity.
All right. And we're just going to use Newtonian gravity, so that's... If this were the case, the thing will drop down on the Earth, yes? Would accelerate towards the Earth? It does not. Why doesn't it?
Because of rotation.
Can you make it more specific? It's true, it has to do with the rotation. But again, if it were just this force, you know it has a force towards the Earth, so it should have an acceleration towards the Earth. It should have dropped down a long time ago in exceedingly speedy fashion.
But isn't that what orbit is? It's always falling just around it.
Well, that is true, but I want to make it more specific. Yes?
There is also like a centripetal force.
There we go. There's a force that's also pushing it backward. You know the formula, by the way?
You said last time. What was it? N times
V squared
V over R, yeah.
That's it. So something is pulling the moon backward, and these two apparently balance each other out, so there's no net force in our direction, right, along this line, and therefore it stays in a circle. What's causing this force? Sorry?
Is it fictitious?
It is a fictitious force. There's nothing here pulling that thing backward, is there? Is there some other source of gravity? Oh, maybe it's the sun or something like that. Yeah, okay, but if the moon is over there, then would it be pulled double towards the Earth if it was just the sun? Something is pulling that thing backward. Yes?
Because of the acceleration, like because it's rotating.
I'm going to make it very specific in a second. So you're right. Here's the idea. This is a fictitious force. And I'm sure that you've seen either in your mechanics course here, maybe, or maybe in your high schools, that you just assume that this thing exists, that if you're moving in a circular fashion that you're being pushed outward. And if you want then to calculate how this thing is moving around the Earth, then you know, oh, you know what? The only way that this thing can have a stable orbit, no acceleration along this line, is to set this one equal to that one. Then do your math. You get something like mv squared over r equals mmg r squared. You do some mathematics and you get Kepler's laws out. Yes? How the moon would rotate around the Earth.
Yeah. I think there was actually a question about this in my high school exam.
Yeah.
Had to learn to drive this.
Yes, but your teacher never told you that he gave you a fictitious force.
Yeah, he called them like was it like a pseudo force or something?
Oh, okay. Okay.
That's what I remember.
Okay. Okay. Well, pseudo force actually already has a meaning in physics, and that's not this one. But I'm sure he meant well. It's conceptually he's right. By the way, something very important for later: the m drops out on both sides, and I will come back to that in a second. So that means that no matter how heavy the moon is, any object by this I mean regardless of its mass will have the exact same motion because the m drops out. This is going to be important later. Now you can do all this and you get the laws of Kepler out, how things move around each other. But this thing is accelerating, isn't it? Because sure, it might go in with a constant velocity, but in a constantly changing direction. That is also a type of acceleration. So are you allowed to use Newton's laws in the rest frame of this Earth, of this moon? If you know that the moon is not an inertial frame, are you allowed to use Newton's laws? The answer is no. So what did your teacher do? He said, well, we are not in inertial frame, so we're going to just squeeze in another force that I just got from somewhere. Assume that it's true and then do your math. This is the consequence of trying to do Newtonian physics in non-inertial frames. All of a sudden you have to add in extra forces. Those are the fictitious forces. What you could have also done is just not go to this frame and look at it from an inertial frame, as in the guy standing backward, not traveling along with the moon, but just seeing the moon move. Then you are in an inertial frame, and then you have a different exercise. Then this one will drop out, right? The fictitious force drops out if you go back to an inertial frame. You've only had this one, but plus its initial condition of going in that direction, and then do your laws of physics there. In both cases, you will get the same answer. But if you go to an inertial frame, you take this as your frame. This is the thing from which you're going to do your Newtonian physics. Non-inertial frame, as a result, you have to, by hand, add in extra forces to compensate. That's the idea. So you have already seen fictitious forces, either called by name or not. Now, to make it a little bit more explicit how this works, and where the expression comes from, I'm just going to tell you the outline. It's very easy to show this for yourself, how to get to this actual conclusion. Let's do it like this. Forget about this one. It's a fictitious force. If you're over here, we're going to look at this from the inertial frame. We're not traveling along with the thing, because then we are in a non-inertial frame. We're going to look at this from the outside in an inertial frame, so no fictitious force. This thing is being pulled inward. Let's give that a red line here. Okay? So that means that the moon is accelerating inward. Yes?
Like if you're like standing on the moon,
Yes.
then technically should you feel any force, because like two forces opposite that compensate each other.
Oh, but you do feel force. Right? If you go to a merry-go-round and it goes faster and faster, don't you feel that you're being pushed backward?
Is that not because of the Coriolis?
No, it's not the Coriolis. No. It's related, but it's not the same. The Coriolis you feel at the moment that you are in a non-inertial frame, and you're also moving in that non-inertial frame. This is where you get the Coriolis force from. It is, by the way, a more involved example of yet another fictitious force. You're right, by the way, but it's a more involved example. If you're on the moon and moving on the moon, you would get an additional fictitious force, which is called the Coriolis force. It's more difficult than we're concerning ourselves here with. Now the moon, of course, wants to, Newton's first law wants to go in a straight line. Note that since I'm looking at this thing from the outside, I'm allowed to use Newton's first law, right? So I notice that this blue arrow exists. It wants to go in a straight line. Now here we go. Newton's first law tells you the moon wants to go in a straight line, blue. Gravity is pulling it inward. Where does it go? If you're being pulled inward, well, you want to go straight. Let's use a beautiful watercolor for this. Listen, I'm running here with a high velocity. And Louis grabs my arm. I want to run in that direction. He grabs my arm. He's the force. I'm Newton's first law. Where do I go? I go through the middle. And depending on how much you go through the middle depends on how strong he's pulling versus how fast I was running. So the net effect of these two is that the moon will go through the middle. And let's say that these two balance each other out in such a way that it exactly goes to the exact middle. If not, you will get an ellipse. Right? This is Kepler's law, so you get ellipses. But let's keep it simple for now. You will go over there. Now the moon is over here. New exercise. Gravity. Newton's first law. Goes through the middle. Now the moon is over here. You repeat this exercise, you get a circular orbit. That's the idea. Do you want to have an elliptical orbit? Fine. Make gravity a little bit less. So it will still go through the middle, but will end up over here-ish. Well, actually that's not a very good example, because it will just spiral out. Let's make gravity a little bit stronger. Okay? Then it will move a little bit more towards the Earth, as if it's doomed to collapse, but because of the gravity, it will have now a higher velocity in a straight line. So gravity will have to work a little bit harder to push it downward now. And if you balance that out, you will get an ellipse. This is the origin of Kepler's laws, that they move in ellipses typically. Anyway, long story short, if you look at this from an inertial frame where there's no force balance, no fictitious force, you also get the circular orbit. Now, you don't have a fictitious force pulling that thing outward, but now you have Newton's first law. Because you're in an inertial frame, you're allowed to use Newton's first law. You get a circle. You don't want to use an inertial frame? Fine. Go stand on the Earth. No blue line anymore, because that thing is standing still with respect to you now. But now you have a fictitious force pushing outward, and you still get a circular orbit. Do you see that it doesn't matter if you are in an inertial frame or a non-inertial frame, you get the same answers out? In fact, you can even calculate this law now. Just the form, I mean, I'm sure that your teacher just gave it to you. There's this force and it has this form. You can actually calculate what it is. I'm not going to go through the whole derivation, it's not very hard, but just going to tell you what the steps are. Let's go to the first situation again. Thing wants to go in a straight line. Here's where it ends up. If it were just for Newton's first law, where would it have ended up?
Where the blue arrow ends?
Yes, here-ish, yes? Agreed? This is where Newton's first law wanted the moon to go. This is where gravity pulled it. Do you see that there's a difference here in distance? And that if you draw this triangle here, you can actually get an expression for this distance. Do you agree? Do you also see that this distance from here to here, it's just the amount of time in between the two moments times its velocity that it was flying? If you play around a little bit with the mathematics, you can get a number for the amount of distance that the Earth, that the moon would have flown and where it actually ended up. So you have a distance. You take the second derivative of that distance because that gives you an acceleration. Apparently, gravity has accelerated, or this combination of things has accelerated the Earth towards here, where it wanted to end up over there because of Newton's first law. Get an expression for this. Use your Pythagoras theorem as such. You get this one as a function of time. Take its second derivative, because second derivative gives you an acceleration. Multiply it by the mass, because mass and acceleration gives you a force, gives you exactly that formula. And you can already tell where the v squared comes from because of Pythagoras theorem. Second derivative, two t's drop out, the t squared, and you end up with this. Yeah, sure, okay. Long story short, if you're a non-inertial frame, you have to build in, by hand, fictitious forces. Again, fictitious forces are no real force in the sense that there's something pulling on the moon or whatever it is. It's really just the difference between where it actually ends up and where Newton's first law wanted it to end up. That turned into a force, gives you the fictitious force. Agreed? As a final step here, do you agree that the fictitious force is always multiplied by m, the mass of the object? Can you see why that is? Every fictitious force will always be m times something.
Yeah, because it's just m times whatever ends up being its acceleration.
Exactly. What I did, just in steps in words now, was I said, well, I'm going to calculate what the difference is in where the thing is and where Newton's first law wanted it to be. Take that difference, take two derivatives, get this acceleration, and in order to make it force-like, I multiply it with m, because m times acceleration is, etc. So that means that fictitious forces are always multiplied by the m of the object that is feeding the fictitious force. Always. Agreed? So this is one way to tell a fictitious force apart from other forces. Fictitious forces always come multiplied with their own masses. Have you noticed that it drops out? And I made the point of that a second ago. That it drops out. Very important step that I'm going to make right now. If you know that fictitious force always come multiplied with a mass. But the mass will drop out. Always. Doesn't that mean that fictitious forces act the same on every object? No matter what its mass is? Yes?
The magnitude is determined by the original force that they're reciprocal to, right?
No. Why would you think that?
Isn't basically like, is Newton's third law, this is action and reaction? Aren't the fictitious forces
No.
basically
I never used Newton's third law, which you're invoking right now. Maybe what confused you is that when I wrote the fictitious force and then I said, oh, it's equal to this one,
yeah.
this is not Newton's third law. This is just a setup of this situation.
It's not the normal force.
Also not that.
Okay.
Normal force is, not always, but sometimes an example of Newton's third law. No, the reason that I said that these are equal was because I assumed in my situation that the moon was not going to crash on the Earth. It's a situation that said that they were the same. There's no physical principle that says I can easily have one of them bigger than the other, it will drop down or spiral away.
So the reciprocal forces are real forces. These are different.
The first word again?
Like you hit something and it hits back, it's not a fictitious force.
No, that is an actual force. Yes. Now, the point that I was making, and that's extremely important, is that once you have a fictitious force, and I hope I've now convinced you that a fictitious force always comes with the mass, and you want then to use this fictitious force in an actual physics example, in mechanics what you always do is you take this, agreed? And then you add in what the forces are that the thing feels. Suppose that this is a fictitious force, maybe this one. Then this one will also come with an m. It will drop out on both sides. Right hand side will always have an m, simply because it's Newton's third law. Left hand side, if you're going to add a fictitious force, is going to have an m, because it's a fictitious force, and they always come with m's. So whatever fictitious force you're going to put in, you will get an answer that's irrespective of the mass of the object. Here's another way of telling if something is a fictitious force. If you throw something around and you see that it moves according to a certain path, and you throw some other thing around that's 20 times heavier and it follows the same path, so it's regardless of what the mass is. Conclusion, then apparently it must have been a fictitious force because mass has dropped out.
So is gravity a fictitious force?
Yes, this is of course where I wanted to go. Because can you name another force that is the same regardless of what the mass is? I have to be more specific. Not the force itself. The path of things is the same regardless of what the mass is. Gravity. Gravity will affect everything in exactly the same way regardless of its mass. In fact, we can prove it right here, right now. Suppose that we're going to write down Newton's second law, but not with a fictitious force, okay, but with universal gravity. Then you see that the masses drop out. And then you can do your math and you get all kinds of answers out, but the answer, the path that the object will follow is irrespective of what mass the thing had. So you have two things now. We have now seen a fictitious force will always have his mass dropped out when you try to calculate the trajectories. One statement. Second statement, gravity by Newton's universal law of gravity will always be the same regardless of what the mass is. So I have two types of forces. Both of them are mass irrespective. What conclusion would you draw?
Gravity is fictitious and mass irrespective.
Yes. Gravity is a fictitious force. This is not a proof, by the way. It's up to experiment to decide whether this is the case. But Einstein said, I have here this one class of forces that only arise at the moment that I'm in a non-inertial frame, these fictitious forces. And I have this other thing called gravity that has exactly the same properties, namely independent of mass. So he said, well, maybe gravity is just a fictitious force that you feel at the moment that you are in a non-inertial frame. That's a very big conclusion. It's a very big intellectual step, if you can make that one.
Can you repeat that?
Yes, but I forgot my sentence. So I'll try, I didn't forget the physics, but I forgot the exact words that I used. Let's try again. Einstein said, I have this one class of forces that is independent of mass, the fictitious forces. I have universal gravity that's also independent of mass. I have to be more specific here. The force itself is dependent on mass. Right? I mean, the formula has an m in there. But the way that particles move, because of that force, has no mass because it drops out on both sides. Okay, so I have two forces, but both share this property. Then Einstein said that maybe gravity is the fictitious force that you feel because you are in a non-inertial frame. If you're in an inertial frame, you feel no gravity. If you go to a non-inertial frame, you feel this fictitious force. That's gravity. That's the exact same properties. Now, this is the conclusion that I wanted to go to at the end of the second lecture, because I promised you that this week I would tell you how to put gravity in our acceleration in our theory, and now you have it. Remember that I said that all of this only holds in an inertial frame. We've now seen that if you go to a non-inertial frame, you feel fictitious forces, and Einstein said, looks exactly like gravity. So Einstein said, we have to rewrite this in such a way that acceleration comes in, and we should get back gravity. That's the idea. This is how you get to general relativity. He wasn't looking for gravity, by the way. The only thing he was looking for was looking for a way to put acceleration into his, that you're allowed to go to a non-inertial frame. That's what he was looking for. But then he found, wait a minute, that looks exactly like gravity. So in trying to expand special relativity to the cases for non-inertial frames, he got back gravity for free. And all of a sudden, general relativity is now a theory of gravity. Yes?
So let's imagine the whole universe will stand still. Nothing will move
With
on.
respect to what? That's hard with the universe, right? But let's assume that. Yes. Continue with the
The
question.
whole universe is like standing still. There's no star or galaxy rotating around something.
Okay.
Then there would be no gravitational force. Like there would not be any attraction or.
No, but you have things within the universe that are accelerating with respect to each other, right?
No, nothing. Nothing is accelerating. Everything is standing still.
What about the expansion of the universe?
Even that.
You just
Not
take a
existing.
screenshot of
Not
the
the-
universe at a certain moment.
Yeah, it's not existing. That's
Yeah.
it's like just to put.
Okay.
And there would be no attraction also. Or
Let me think about it for a second, because what you're looking at here is something that we call Mach's principle.
okay.
And it's an unresolved question in theoretical physics, and one of the reasons that it's unresolved is simply
okay.
because it's hard to do experiments on things outside of the universe looking inward.
Yeah.
But it is a very valid question. If you look at the universe as a whole, does that thing accelerate, and or does it come with its own gravitational forces built in? That's a good question. First, let me just give a point-wise summary of everything that we see now so far. Okay. So this we have, yes. We saw fictitious forces. I love these lectures where I get off my original written down path and we just end up getting to the same results, but now, fed by how we're discussing this. Fictitious forces always are proportional to the mass. Gravity is also proportional to mass. By gravity I mean Newton's universal law of gravitation. As a result of fictitious forces being proportional to mass, that means all particles or all masses, all objects, regardless of their mass, will move the same due to a fictitious force. Right? This is this example that I've used before. A fictitious force in Newton's second law is m times a. This thing comes with the mass, so mass will always drop out, and the acceleration will be the same. Your physics will be the same. So always are proportional to mass. So the path of the masses, by path I mean the x of a function of t that you find if you solve this differential equation, is independent of n. Same conclusion here. Right? Conclusion. This is Einstein's conclusion, the big step that he made. Therefore, and here's that difficult sentence again. Gravity is the fictitious force that you feel because you are in a non-inertial frame.
But
Yes.
for example, in the with the roller coaster example,
Yes.
if you were to throw another stroopwafel, that it will feel a fictitious force, but it's not gravity, right?
Can you say that one more time?
The stroopwafel, it would seem as it's feeling a fictitious force, right?
Yes.
But that's not gravity.
No, it's independent. You cannot tell by looking at the thing by itself. I mean, you in this my particular example with people in a ride, you can say, well, I know that there's a planet here, so I know there's some gravity stuff going on, something like that.
Yeah.
That is very true. But suppose that you're somewhere in empty space and you let your stroopwafel go and it will accelerate backwards. Then you cannot tell whether you just happened, you yourself and your stroopwafel being in a non-inertial frame and it's just Newton's first law trying to hold the thing back, or that there is some enormous amount of mass with its gravity putting the stroopwafel backwards.
Okay.
That difference you cannot tell anymore. So Einstein said, that's this statement. Every force of gravity is indistinguishable from you being in a non-inertial frame. It will have the exact same effect on your stroopwafels. Now all of this, this is the main conclusion. I mean, if you take away this from today's lecture, then I'm very happy, because this is where general relativity starts. Now, all of this hinges on one detail, and that is that this one is true. If you find that there are masses around that fall differently due to gravity, so if this is not true anymore, then the forces, you can tell a fictitious force apart from a gravitational force, because this one will still be independent of mass, and if gravity does depend on mass, it will still look different. Now, this statement, again, I want to come here via a different route, but here we are, is called the equivalence principle.
Oh, we've done that.
Mm-hmm.
You have?
The special relativity.
Oh, you did, yeah?
But it leads to like a very tentative conceptual general relativity in that one as well.
Okay, well, what did Chris say about the equivalence principle? It was Chris who taught that course, I think.
Mm-hmm.
I don't remember, it was too long ago.
I think he basically said what you just were talking about.
Okay.
And when you throw a stroopwafel up, you see it moving backwards, you can't tell if you're in an inertial reference frame or if you're
Yes.
feeding it.
That's exactly this statement.
Yeah,
The fact
that's-
that these
that's-
two,
That's what he told us.
the fact that these two give you the exact same results,
Mhm.
Distinguishable.
that indistinguishable, that this one you cannot tell apart from this one. Again, with the right example, it's very simple because you can see the planet and such. But just from the motion of the stroopwafel itself, you cannot tell the difference. That fact is called the equivalence principle.
It's a uniform gravitational. It's a uniform gravitational field feels the same as a non-inertial frame.
Yes.
Something like that.
Is that the way that he put it?
Yeah.
Okay, well, there we go.
Something good.
That's a uniform gravitational field. We're smuggling in a new word here, by the way, but it's okay. A uniform gravitational field is indistinguishable from being in a non-inertial frame. That's this statement again.
if you fall into the earth and there's a rocket sending you to the earth, the mass accelerating you towards the earth, the mass are the same.
Yes. That's true. I mean, if I would jump off the building and somebody would throw a strobe after me, and let's say that we start at the same time, because my mass and the strobe mass drop out of our acceleration, right? If you do Newton's calculations and you find that the strobe and me have the same acceleration, forget about air friction, because that will make a difference. Do away with air friction. Then me and the strobe will drop down with the exact same acceleration, and me just looking at the strobe is not enough to tell whether we are in a gravitational field or that we're in a non-inertial frame. Again, that's the equivalence principle. That's the whole idea. Now, the equivalence principle you can simply test. You drop any two objects, make sure that there's no gravitational field, no other field, no other influence than gravity. And if you find that they drop at the same rate, then you know that this is true, and therefore these two are indistinguishable. So this is just something you can test. Let's do it here and now. This is a test you might have seen before. It's one that's very easy to perform. You need a very heavy object. It not being my laptop. It's going to drop on the floor. Will it hold?
Yes, it's plastic.
Okay. How the lid is synthetic?
It's very steady way.
As long as it doesn't spill over anything or anyone, I should be fine. Okay, well, here we go. I have two objects here. This marker and the water bottle. Gravitational field, yes? Okay. Went down at the same rate, even though that thing is, I don't know, 3-4 times heavier or something like that. Alright, so as far as this experiment tells you, gravity really does make everything fall in exactly the same way, which is that thing that I put the marker line. You have to check whether that is true. If that is not true, you cannot draw that red conclusion. Now, experiments tell you that it really is the case. Now, same exercise. And we've now broken general relativity. That sucks. There's a reason that I'm showing this, not just for the statement's sake. So why didn't they drop down it with the same rate? Because that is my claim that should happen. It's air friction, right? So this only holds if you have just gravity. Any other influence will ruin this statement. But just gravity and gravity alone will make the equivalence principle hold. Now, of course, you can demonstrate that too. The only thing you have to do is remove air friction, or make sure that the air friction for both of these are the same. We can also, make this whole lecture room vacuum. I think this is easier. I've made the surface, this ball, made a little bit smaller. So that means less surface, less air friction. Same mass though, mass hasn't changed. And if the equivalence principle is correct, that if gravity is the only influence, or somewhat differently stated, if all other influences are the same for both, then they should drop down with the same rate again. And there you go. So this statement, this one, you can actually test that it's proportional to mass, or in other words, that it drops out. So that it's mass independent. You can test this, test this, test this. One of the best tested theorems in all of physics. I think they're down to what, 10 to the power minus 10 accuracy or something like that. It really holds. And because this holds, therefore its trajectory, the A here, is independent of mass. This is independent of mass by construction, therefore Einstein says should be the same thing. That's the whole idea. Yes?
Isn't the fact that gravity is not affected by mass a classical idea?
Yes.
You can derive it from classical mechanics.
Yes and no. Yes and no.
The masses and the accelerations.
Well, yes, but
Yeah, mass law.
let me make one statement about that. Can you derive it from classical physics? The answer is somewhat yes. Here's Newton's second law again. And you just put in Newton's universal law of gravitation. Okay, now where this comes from, this is called an experimental statement. And what I do is I just cross out m on both sides, and therefore the result, whatever it is, will be independent of m. Okay? But it does come with one assumption, and that is that this m has the same value as that m. And then you might say, of course it is, because it's both mass, right? But if you think about it a little bit more carefully, this mass plays a completely different role in physics than this one does. This one is a mass or some number that tells you how strongly the Earth or whatever is the cause of gravity is pulling. This mass, let's take mine, I have to weigh myself 2 weeks ago, it was 90 kilos. So this number called 90 in this formula tells me how strongly the Earth is trying to pull me downwards. This number m tells you how strongly my mass is trying to resist itself against acceleration. That's two completely different things. One mass tells you how strong gravity is pulling, the other one tells you how strongly you don't want to accelerate. It is not obvious whatsoever that this number is the exact same numerical value as that number. And for that reason, purists give these different names. They call this the gravitational mass. They call this the inertial mass. And again, it's not obvious that these numbers are the same thing. Now, the fact that apparently up to 10 to the power minus 10 in experiment, these numbers are the same, means that you can drop them out and then you come to this conclusion. So one other version of the equivalence principle that people use is this. Equivalence principle says that gravitational mass is the same number as inertial mass. That is one other formulation of the same principle, because that leads again to all these conclusions. So. We're now at a very important point in our lecture series. We now know how we're going to build in gravity. The only thing you have to do is take this, that only holds for inertial frames, find out how it works for non-inertial frames, and if the equivalence principle is correct, it will have given us gravity. And that's the idea. Now, small comment before we take a break. The fact that it apparently, according to this principle, it is connected to gravity, gave Einstein a very strong hint on how he should build acceleration into this. Because he knew that acceleration, in a number of cases, should boil down back to Newton's gravity. So he sort of already knew how he should build in acceleration. From now, for acceleration, you can read gravity, how you can build in gravity, because he knew that it should be related to this formula here. That gave him a very strong hint on how to rewrite this in a non-inertial way. Okay, whew, big steps today. Any questions? All right, then I propose a break. Serious equivalence principle. Gravity is indistinguishable from the fictitious force a mass experiences when in a non-inertial frame. And as I hope we've convinced you, that's the same as saying that there is inertial mass, gravitational mass. These two numbers are really the same number, because only then you can cancel them out on both sides of the equation as such. Now, just for a little bit of nomenclature, it is important, but not to focus too much on it. This is, if you will, something that's called the weak equivalence principle. And as you can imagine, there's also a stronger version. Any idea how that one is called? Strong. Yes, I set you up to say that. It's called the middle strong equivalence principle, because there's also a strongest version. This you can test in the laboratory. Really what it says here is that because mechanics, Newtonian or relativistic mechanics, is independent of mass, then therefore gravity is indistinguishable from non-inertial frames and such. That's called the weak equivalence principle, if it's just mass who does that. But Einstein took two bigger steps. One step that he took was But what if it's not mass that you're trying to describe through, that moves through space? Suppose it is, say, electromagnetic radiation. Does for electromagnetic radiation it still hold that electromagnetic radiation in a non-inertial frame gives you the same results as gravitational electromagnetic radiation in a gravitational field? This you cannot test by doing this experiment, because electromagnetic radiation has no mass, right? So that is called the middle strong equivalence principle, that not just masses move through space under gravity as if they are in a non-inertial frame, but that all of physics does. I took electromagnetic radiation as example, all of physics. So thermodynamics, electromagnetics, all these things. Quantum mechanics, blah, blah, blah.
What's the strong one?
Yeah, that's the one there's some hierarchy there, yes? I mean, all of physics and then some extra maybe. Gravity itself, say a gravitational wave, that even gravitational waves cannot tell the difference between being in a non-inertial frame and being in an external gravitational field. That's the strongest version. Now this one you can very easily test. Agreed? You just drop things. Gravitation or electromagnetic radiation, a little bit more difficult, but you can still do the experiment. Gravity itself, at this point, is an assumption. That even gravity itself cannot tell the difference between non-inertial frames and an external gravitational field. And yeah, in principle, this is open to debate or to experiment. And you can imagine that one of the things that people do now when they test the theory of general relativity using this gravitational radiation that we can now detect as of 2 or 3 years ago, this is one of the tests that they do. In fact, there is one subgroup in the Ligo-Virgo collaboration that is called testing GR, testing general relativity. And one of the biggest things that they do is find out whether the strong equivalence principle holds. This one you can test. Electromagnetic radiation you can also test. Gravitational radiation in a gravitational field, much more difficult. And one of the ways that they do this, so you know what people are working on these days. Remember in October that they had a colliding neutron star, 2 colliding neutron stars, etc. It sends out gravitational radiation. The reason that people found it so ridiculously interesting was not so much because there were 2 things bumping into each other making gravitational radiation. That was, very blasé, already known by that time because we had already seen a number of black holes colliding into each other. So the gravitational radiation part, that part was not new anymore. I say this in a very blasé-like fashion because there was only like the 6th detection that they ever did. But by that time I said, well, we already know about gravitational radiation. The reason that they thought the neutron colliding stars was much more interesting is because they also send out light. So what they did was, they measured the gravitational radiation, they also measured the light, and then they checked if the light and the gravitational radiation moved the same through space on their way to Earth. If they did, that's a test of the strong equivalence principle. Because if gravity would have not obeyed this principle, this gravitational radiation, it would have moved in a different way. So they needed something external to compare the gravitational radiation detection with. And they took light. You cannot do it with black holes, but you can with neutron stars. Now they found that as far as they can tell, as far as the experiment allows it, the experimental inaccuracy, the strong equivalence principle holds. And that was the first test of strong equivalence principle. Now, of course, the media picked up on these colliding neutron stars because they said, oh, there was all kinds of gold created, which is true. But that's simply because if you're on TV, you have to explain why this is an important thing. Then saying, well, we've tested strong equivalence principle is not as media friendly as saying we know where gold comes from. Yes?
But light can also travel slower than light, right? Because it
yes.
encounters
Yes, but it doesn't encounter anything on its way here. No, there are no clouds in between. The only thing that it encounters, both the gravitational radiation and light, the electromagnetic radiation, was the external gravitational field of the universe as it was traveling towards the Earth. To put some numbers to it, they found that the delay time between gravitational radiation arriving here and then a moment later the light, the electromagnetic, was 1.7 seconds. But that was over a distance of, I forget what the number is, but I think it was 1.3 million parsecs or something like that, some big number. So you have to imagine that this thing has traveled for millions of light years, these 2 things, and they haven't catch up on each other. So that means that they probably have moved in the same way. That's one test, their arrival time. There's still 1.7 delay, but that's because light is emitted a fraction of a second later. Now, if it had been that light would have moved different through a gravitational field, external gravitational field, than gravitational waves themselves, you would have expected in 1.3 million years or whatever it was, billion, I forget the number, but some big number, that the lag was much more different. Even in the smallest amount of difference in velocity between the two, or their response to the external gravitational field, you would have expected a huge difference in arrival time. It wasn't there. That's one of them. The other one is how much it was deflected on its way. And there was none of that either. So that's a test of the strong equivalence principle. That's a very important discovery. That's very, very new. That's literally only months old. Yes?
Is this related to gravitational lensing?
Yes, they were lensed in both the same way. The external gravitational field has pulled light, the electromagnetic radiation, and the gravitational radiation in the same way. And because it did in the same way, there's a number for that. It's called gamma that measures that. It's not the gamma our Lorentz gets, it's a different gamma. And because they were pulled in the same way, it's again a test that apparently gravitational radiation itself, gravity itself, and the rest of physics obey the same principle.
So that the picture deformation would happen with its mass measurement as well?
Yes.
Equivalent.
Yes. If we could measure gravitational waves in the same way that we can do light, we can measure them but not quite in the same easy way, you would have gotten this, you know, these Einstein rings that you get with light, you would have had the same thing with gravitational radiation. But we're not experimenting there yet. So you could also do that. If suppose that you have this Einstein ring and you make one of light, and suppose that our technology is good enough that you could also make an Einstein ring of gravitational radiation itself, and they completely overlap, that's a very strong indication that the strong equivalence principle holds. This is why it was so important. Or one of the reasons, there were many, but this was one of them. Anyway, so for now we're going to assume the strong equivalence principle. So forget about this one. That's only our step towards. We're going to use the strong equivalence principle from now on. Alright. Now, back to some formulas. So this is the key thing. Back to formulas. Let's write down the line element again for just normal Minkowski space-time. Here it is one more time. That thing is invariant. I'm going to park this for a moment and get back to it later. Okay? I just have to make some mathematical steps here. The steps I'm going to take are just mathematical, and only mathematical in the sense it's new notation. Again, the electrodynamics people have seen this. New people are going to see this probably for the first time, maybe not. In all cases, it might be a good reminder. This invariant, we're going to write this in a completely new way, and it's going to be extremely economic. At the moment, we're going to make the transition of these kinds of formulas to general relativity. We're going to write this as such. I'm sorry, this is just something that we'll have to accept for now, because again, there's no physics, it's just notation. This is the same expression. It's just I introduce a new notation. Here's the notation. Yes?
Sorry, it's eta, right?
No, this is mu. Oh yeah, this is an eta.
Yeah.
That's true. This is the Greek letter M. I'm sorry if I botch up your alphabet, but this is okay. Thank you. This is the Greek letter N, and I think this is eta, and I'm probably also botching up the pronunciation. But
It's eta, officially an eta.
it's eta.
Eta.
Eta. But did I say eta?
Oh, it doesn't matter.
And nu,
Some people decided to give this Greek letters. Yes.
nu is just like a u.
Well, not really. It's
more like
it's
a
how about
that's the mu. But
That's the mu.
The
Yeah,
other one
and
looks
u,
like
I write as a V with a little thingy on top. But really, my Greek handwriting is very bad. Fortunately, most physicists' Greek handwriting is very bad, so people understand what I write down when I write down this, okay?
I have a question.
Yes.
Out of simplicity, it's not possible to change mu and u.
Yeah, sure, you could
Because we
IJ.
had that this last time when we like confused about.
Yeah. Oh, yeah, that's true. That is true. I thought maybe you want to have Roman letters just for the handwriting, but no, you mean something else.
Yeah, because if you were talking about mu,
Okay.
mu,
Okay,
mu,
let's do that. No, he makes a good point. In electrodynamics, the course, we also switched to this notation because we made the step from electrodynamics, electromagnetic fields, to relativity, and I introduced this as well because this is the way that you write these things. And then Louis at some point asked, well, but the mu and the nu, just by pronunciation, sound very much alike. So.
What about M&N?
So, sorry?
What about M&N in English?
No, because this is just convention. They use Roman letters for the spatial part, and the mu and u, the Greek, are reserved for space and time. So these are already reserved, M and N. But we came up with the brilliant idea to not use mu and u, but alpha and beta. Still Greek, but at least they don't sound alike.
Mm.
Okay, maybe that's a good idea.
No, but after it makes it easy if you explain that if new is like applying to something that
Yes.
not confused.
No, I agree. That was a point that we had last time. It's hard to tell them apart in speaking. Unfortunately, people use mu and u as their default setting. I mean, I'm happy to use this, but be prepared that if you open a book, you will find mu's and u's. Let's do alphas and betas. That's a good idea. In fact, I think we even promised that we would do that next time. So here we go. Okay, this is just notation. There's no new physics. There's not even new mathematics. It's just a new notation. Now, what is notation? It's as follows. dx with the Greek index on top is shorthand for 4 numbers in a column as a vector. This number is c times dt. This number is dx, dy, and dz. So that the whole dx alpha is one big shorthand notation for all these 4 things. In the same way, dx beta is the exact same thing. Yet there is a difference between alpha and beta. Not in these expressions, this is just really the same thing. What the alpha or the beta does is just label which of these 4 you mean. And it's very economic because we will find expressions where all 4 of them are meant. And instead of writing down 4 equations for each for dt, for dx, dy, dz, you just write down this and you find the equation that holds for all. So it's economic that we do this. There is a difference between alpha and beta here, and that is in this. We make the following rule, notational rule. Once you have, and there we go again. Let's do that like this. Once you have an alpha in some expression with a Greek index alpha upstairs, as we call this, and you find it also has an alpha downstairs, it means one thing. It means that you take alpha to be this one, that one, that one, and that one. Calculate what you get for each of these values, and then add all these things together. That's abstract, isn't it? So the best thing is just to write it down, so you see what happens. It takes a little bit to get used to, but once you have gotten used to it, it's by far the easiest way, not just to do calculation, but also to see what's going on. So let me make one more, as a little side note. This is what we call the Einstein summation convention. Again.
Sorry, Garen.
Yes.
Is there a subscript, the alpha and the beta?
Yes.
For the,
Here it is.
for the eta? There's subscript for the eta?
Yes? Oh, no subscript, no.
That's fine.
Just superscript.
Normally.
Yes. Einstein summation convention. It means once you have a repeated Greek index, so 1 up and 1 down in an expression, it means take every value of that Greek index. That's 4 of them, right? 1, 2, 3, 4. Take each and every one of them. You get 4 separate expressions. Add everything together. This is a crappy example. Suppose that you have A with an alpha. By this I just mean some object with 4 numbers. I have no idea what to call them, but 4 of these things. And suppose that you have another one, beta, again with an alpha. Again 4 numbers, and suppose that you put one of them upstairs and one of them downstairs. Then by definition, what is meant is the following. Minus, I will give them names from now on. This I will call alpha 0 or A0. It's just some number, okay? 4 numbers in a vector. And this is called A1, A2, and A3. B0, B1, B2, B3. Why not 1, 2, 3, 4? Convention. Yes?
And we'll also just use the letters. Like
In what
T
sense?
for time and X, Y, Z.
Yeah, sure. This is used interchangeably. That is, say, A time, AX, AY, AZ. You could also use that.
Which one are we going to use here?
We can decide here and now. Let's stick to the numerics right now. Okay? Again, this is notation, no physics. What this means by definition is, take this A vector, let alpha be every value that there is. Now, one value for alpha is 0, yes? That's one of the 4 values here. Put that in, this number. Multiply it with B, but with that same number, which is 0 in our case. B0. Why the minus? That's the notation. You do the same thing for alpha is 1. What would you get? You would get B1, excuse me, A1, that's this one, times B1. What I've done now, I've taken these two, but alpha is equal to 1. I get this number. In the same thing, do it for the number 2, A2, B2. This is not B squared, it's the second number in that column. And finally, A3, B3. There you go. And again, this is just what this notation means by definition. This one means add everything together. This one comes with a minus sign.
Because of the eta?
Sorry?
Because of the eta?
Yes, I will introduce the eta in such a way that will keep track of your minus sign. That's what I will do. Yes?
Can we put the first one positive and all the other one negative? So
Yes. Last week what I told you was there is some convention going on in where you put the minus sign. Both of them are fine as long as they have a relative minus sign. You cannot have minus, plus, minus, minus.
So we could use the same logic as for the...
This is the reason why I introduced this. I'm going to write what we have here in this new notation. Yes. Yes.
I didn't really get why we put the alpha like down, not in uppercase. What will we change if we put in uppercase?
Yeah, well, that is exactly what I skipped when we did relativistic electrodynamics. I sort of use them interchangeably, right? There is an alpha downstairs here, and there's an alpha upstairs there.
Because we saw that both the delta upstairs give the same.
Yeah.
So,
Well, again, I'm very sorry. This is just a notation that people use. There's no physics here. This is just notation. Alpha mu with downstairs, that's not this thing. This one has all the numbers upstairs. Alpha mu is, again, just notation, means that it's minus A0 plus A1, A2, A3.
So if the alpha is like in uppercase, then the minus would not be there.
Yes.
And the other ones would have then.
They would have still have pluses.
Okay. Yeah.
But if you look closely, this is what I'm doing, right? I'm taking alpha 0 down, but alpha 0 down is minus alpha 0 up. This is where this minus comes from.
Is that the anti-covariant one?
Yeah, that's that difference.
Okay.
But I decided not to use those names here. It's, but you remember from back then, yeah, it's the same thing. Well, that is crappy notation, isn't it? One thing that is crappy about this is that you constantly have to wonder for yourself, wait a minute, where's the minus sign again? So people decided to give this a somewhat bigger way of notation, but still the exact same expression, and that's the following. Same expression. It still means minus A0 B0 plus A1 B1 plus A2 B2 plus A3 B3. This is exact same expression here, yet another notation. Now why this other notation? Because now if I write down this, I have to remind myself that one alpha has gone up and one of them has gone down, and you have to remind yourself constantly where the minus sign went. So what people did was introduce this thing to keep track of your minus sign. This thing is called the Minkowski metric, for reasons that I hope that I will convey to you today. Minkowski metric. Maybe you can already feel why that is. We call this the Minkowski line element. And one thing that we saw that you needed for this thing to give you back all special relativity was this these minus signs here. If you do away with these minus signs, that was Andreas' question last time, what if they were all pluses? You get different physics, and unfortunately not the physics that nature has decided to use. We called this, with the minus signs, we call it the Minkowski metric. So keeping track of that minus sign, we call the Minkowski metric. Now what is this thing? It's a matrix. It's a 4x4 matrix with numbers in there. This is the Minkowski metric. Newcomers to this notation, do you understand that this thing does indeed give you that? If not, we're going to go through it in detail. If you have a thing like this with only one index, it just tells you which of these four numbers you mean. Agreed? You have here one that has two of these indices. So just having four numbers going down is not enough. That just gives you the alpha. You have another beta. Well, given that you've already used the downward version of writing things down, there's also the horizontal one. So alpha beta just designates which of these 16 numbers you mean. And the notation is as follows. This is the 0th row. Here's the first row. Second. Here's the third. These are labeled by the alphas. If you say alpha is 3, you mean 0, 1, 2, 3, you mean this row, that you're operating in this row. Now you also have columns. Do you mean this column, that one, that one, that one? Those are the betas. This one is the 0th column. This is the first column. That's the second column, that's the third column.
Is there convention as well? Calling the first 0th row is 0th row?
Yes.
Can it be arbitrarily changed?
If you want, you can call it 1, 2, 3, 4.
Yeah.
Sure. And there are some books, but they're in a high minority that use 1, 2, 3, 4.
So in linear algebra, I think that they were numbered as 1, 2, 3.
Yes, but there's a reason that we do this in linear algebra. You might have seen in linear algebra that they start counting with 1, 2, 3, and not 0, 1, 2, 3. And the reason is that the 0 has something different than the other ones. The 0 parts always come with an extra minus sign. So if you say 1, 2, 3, 4, you might give the impression that it's really just the same sort of stuff, but it isn't. And 0, this is just me talking, but I mean 0 is not quite along the same lines as 1, 2, 3.
Makes sense.
Again, it's just notation. But so when I say, for instance, eta 1, 3, I mean the number in eta in this matrix. 1, 3 means first row 0, 1, third number 0, 1, 2, 3. So eta 1, 3 is 0. So this is a convenient way of writing 16 numbers into one expression. Wow, we're still doing just notation. You might think, well, this is an enormous amount of notation just to memorize where this minus sign is. You're better off just saying, well, here's a minus sign. Okay, Maybe you can already tell why I'm introducing this, not just for economic reasons and don't have to write down 15 equations all the time. There's another reason. In general relativity, this line element will be replaced by different numbers. You don't get -1, 1, 1. You get multiple numbers. In fact, they might be functions themselves. And from that moment on, this is to remember just a minus sign. Replacing all these zeros and minuses and ones by functions themselves gives you a huge mess, and you're better off writing this. So right now it's an overkill of notation, but once you have the notation, it's very easy to make the step to general relativity. Now, just to prove, again, this is just the introduction of the notation, just to prove that this expression is really just this, just do the writing out. I'm going to do part of it here. My claim is that this, with this new notation, is indeed exactly this expression.
Isn't that second alpha supposed to be a beta?
Yes, this should be a beta. In fact, this is how you can tell that somebody made a mistake. If you have more alphas or betas than you can do this notation with, then you know that somebody messed up. Alright, again, just introduction of notation. The rule is, if you see an alpha upstairs and downstairs, that means alpha should have every value and then all these contributions added. Note that you have two of these notation issues. Alpha alpha, we also have beta beta, so you have to use this trick 2 times. Let's start with the alpha trick first.
Wait, so
yes.
Sorry, I'm not sure to get what you mean by like the convention about the small letters and.
I'm not sure what your question is.
What you just said.
Yes.
Right? With the subscript and the other one.
Yes. Oh, the notation convention.
Yeah.
Well, let me write it out. It's easier shown than told. What it means is take alpha to be all of the 4 values, 0, 1, 2, 3. Then you get 4 contributions. For each of these alpha values, you get 1 expression. And then the convention says, add all of these together. So that's what I'm going to do right now. I'm going to leave the beta for now. That's the second step. Let's start with the alphas first. Again, notation convention says alpha has to have all 4 values. So one of them is alpha is 0. Again, I'm going to leave the betas for now. So beta is still beta. Alpha has to be 0. And the betas I'm going to leave for now. That's if the alpha has one of the 4 values. But it also has the value 1. Here's alpha is 1. If alpha is 1, then this A alpha becomes A1. And the betas I'm going to leave for now. Here's eta 2 beta. So alpha has now become 2. That gives you this contribution, and the betas I'm leaving open for now. And finally, this one. So far so good. This is just me using what the notation means, what the convention means. And I said, take the alphas to be every of the 4 values and add these contributions together. Alright? This is one of the 2 Greek indices that I've dealt with. Now the beta.
Here the beta is some constant, or you haven't shown that yet?
What do you mean by the beta as a constant?
Because you're only indexing the alphas.
Yes. And I've taken, I also have to index the betas.
Are you showing it separately?
I haven't done it yet. That would be a next step.
Oh, it's a separate.
Yeah, it's a separate one. This is what I said. You have this rule that you have to add the different values for alpha and add them together. I've only used now for alpha, but there's also a beta, so you have to use this rule twice.
And it's separately you do the betas.
Yes, and that's what we're going to do now.
And in this case, we don't need the negative.
No. The negative, I told you, is encapsulated in the eta. The eta will make sure that the negative comes at the right place. Okay, well that's crappy because now we have to do the beta as well. But you already saw that, well, the beta has 4 values, so that means that this will split up in 4 expressions that you have to add together. So this one will turn into 4 if I do the beta version. By the way, this is called a contraction. Taking two of the different alphas and having all of those is called a contraction. So let me use that word from now on. If I do the beta contraction here, this one will split up into 4 separate pieces. This one and that one. So that's 16 pieces. That sucks. So feel free to write it out. All right? Let's be a little bit more economic here. Because let's just look at this term here. You have eta, 0, beta. So that means in the eta matrix, the Minkowski matrix, you're already in the 0th row. You're operating here. This is beta 0, beta 1, beta 2, beta 3. What we're going to do now is take all of these 4 values and add these together. Now do you see that the beta 1, 2, 3 will be 0 times something? You're not adding anything. So again, the alpha here is 0, so that means that you're in the 0th row. So you only have to deal with these 4 numbers. But 3 of these numbers will give no contribution. Will give you 0 times something, which is a 0 contribution. So that means the only beta that you're concerned with is when beta itself is 0. That's the only non-zero in this whole row. So sure, I'm free to write all the 4 beta expressions and then look what the numbers are. I could also just be convenient and say, wait a minute, in this row the only one that's going to make a contribution is this one. Beta is 0 and the other betas will give me nothing, which is add zeros. And just immediately write down that the only beta that matters here is beta 0. And this beta also becomes 0. Agreed? So this is in principle 4 terms. It just happens that 3 of these 4 terms are 0. And I've only written down the one that matters. Question. What is the value of eta 0, 0? 0th row, 0th column. That's -1. Okay. That's this -1. Now you can play the same trick with these, this is the first row. So we're now looking at this one. This one has been taken care of. This one we're looking at now. 3 contributions of the 4 will give me 0. There's only 1 contribution that does not give me 0, so that's the one I'm going with. Which beta is that?
1.
That's beta 1. So this contraction will give me A1 and then B1. What is the value of eta 1, 1? That's 1. So here's this +1. That's this one. Now you continue this game and you end up with this. And this is what I promised, that this is a shorthand notation for this, given that you know how this notation works, and making sure that you have the matrix. And then the matrix will make sure that you get the -1 in the right place. Okay? Huge overview of notation, isn't it? But again, it becomes extremely economic later on. One final comment. Here's a claim that I'm making. Do you agree with this? It's true. This is a true statement, and this we're going to use many times over. But given what we have found now, just our new notational scheme, this should be somewhat obvious to you now. That a vector with a beta downstairs is the same as the thing with upstairs with this Minkowski matrix in front. But let's write it out, just to be sure, okay? Suppose that beta is 0. Then my claim is that this should be equal to eta with beta 0, here's still an alpha, This for beta is 0. You have two Greek indices now, so you have to use our notational scheme. What do? What does it mean when you see one index upstairs and downstairs? This is what I call the contraction. It means take all 4 values, alpha 0, 1, 2, 3. You get 4 contributions, add them together. This again is what it means when you have one upstairs and downstairs. This is our new notation. Well, let's do it. You get alpha, eta 0, 0, alpha 0. You also get eta 1, 0, a1. Eta 2, 0, a2. Eta 3, 0, a3. And you add everything together. This is what the notation means. This here is our definition of that notation, that contraction. What is eta 0, 0? It's minus 1. What is eta 1, 0? Let's look at the matrix. First row, 0th column.
0.
That's this number. First row, first row, 0th column, 0. So this is 0 times a1. Here what I need is eta second row, first column. Second row, 0th column, excuse me. That's another 0. So this is 0 times a2 plus 0. Last one, eta 3, 0, third row, 0th column. Third row, 0th column, that's this number, another 0. So apparently, a0 with the index downstairs is the same as minus a0 with the index upstairs. Man, lots of notation. I did this now for beta 0. What if beta is 1? Maybe you can mentally go through the exercise. What would you get if this is not a1 downstairs, a0 downstairs, but a1 downstairs?
You would not get the minus.
You will not get the minus. If you go through the exercise again, just write out this notation and look up the numbers in your matrix, you will get a plus. Same with a2 and same with a3. Long story short, the way that people describe this is they call this raising or lowering the index. If you want to have the Greek index going from upstairs to downstairs, just put the Minkowski metric in front. It makes no difference if the thing that you were looking at was 1, 2, 3, we just get back the same number. It will make a difference if you're looking at the a0, because that one gets a minus sign.
Does it also work if you start by making the alpha equal something?
What do you mean? If you
started by making beta equal something, does it also work if you do alpha?
Well, you're not allowed to, because the alpha, by the definition of notation, has all 4 values added together.
Oh.
So you already have all 4 of them.
Okay.
Confusing?
But just before you changed it,
Yes.
in the square, so if a subscript 0 is equal to what again?
To minus that one. Now, what do I want you to remember from all of this? Is first of all, every time you see an index upstairs and downstairs, make sure that that index has all 4 values and add all contributions together. Your eta, your matrix, will tell you where the minus sign goes. Don't put it in by hand, the matrix does it for you. Secondly, what I want you to remember is that if you want to bring down this index, you want to make sure you want to make it go from upstairs to downstairs, put the Minkowski matrix in front. And then you'll get the same thing back with the thing downstairs.
Why would we want to do that?
You don't really want to, because instead of writing things downstairs, you could also just always just write this Minkowski matrix in front. But some books do away with the Minkowski matrix because they, by definition, put it already in the downstairs version of these things. So if you read an article, or maybe even the book, because they use that too, and you see the index downstairs, you might think, wait a minute, where did the Minkowski metric go? It's by definition built in there. This is why I'm showing you this. Now, here we go. Now my claim was, this is just notation. My claim was that our Minkowski line element can indeed be written in this way. Do you see that this, if you write down this using our new notation, alpha, here's an alpha, that means you have to use this notation, this contraction, right? Let alpha be all four values, 0, 1, 2, 3, add everything together. There's another one, a contraction of the betas here. Give beta the values 0, 1, 2, 3, add everything together. You get 16 terms in total, 4 because of the alpha contraction, 4 because of the beta, in total 4 times 4, 16 terms. And then the etas will make sure that a lot of these terms are themselves 0, because the eta comes with all these zeros. And ultimately you will just end up with this. The same thing. So do it very quickly, because we should be able to figure this out now. Again, let's do the alpha contraction first, leave the betas for now. Do you agree so far? This is me giving one step in between. This is me taking alpha to have the value 0 to 3. This gives us these 4 terms. I've left the beta for now, the beta contraction. So this is me using this notation once. You have to do it twice because the betas also contract. We saw before then, well, this one splits up in 4 terms by itself. Every beta value have 4 terms. Another 4, another 4, another 4, 16 terms. Feel free to write them all down, or just be smart and think, wait a minute, eta 0 beta means that you are in the 0th row, and then go through the 4 columns. And the only one that matters is the -1 one. And the other ones just give you zeros. So this beta contraction, the only one, it's 4 terms, but all terms will be 0, except when beta itself is 0. You get eta 0, 0. What's the value for eta 0, 0? That's -1. Okay. But then you get dx0 times another dx0, dx0 squared. Agreed? What is dx0?
CDT.
CDT. So there's that. We've taken care of this one now. Let's do one more. This, if you do the beta contraction, you get 4 terms. Beta 0, 1 to 3. But feel free to write them all 4 down. You could also say, you know what? We're in the first row now. First row. There's 3 numbers there. 0, 1, 2, 3. But the only one that gives a contribution is the beta is 1. The other ones just give you a 0 contribution. You might as well not write them down. So you get eta 1, 1. What is the value of eta 1, 1?
1.
That's 1. Okay, so that gives you dx1 times another dx1, because beta is now 1. dx1 squared. What is dx1 squared? Here are the dx's.
Dus de dx squared.
That is just dx squared. To play the same game here, the only eta that works here is when beta is 2. That gives you another 1. That's true, that gives you another 1, that's this one. Gives you dx2 squared. dx2 is dy, and that thing squared. And this one will give you dz squared. And my claim was this is equal to c squared d tau squared. Am I right? This is the moment when I see people are awake.
Oh. Minus.
Oh yeah.
I think
Minus.
my dt should come with a minus, with a plus, and the rest should come with minuses.
Okay. Yeah.
I haven't done anything. Literally the only thing I've done was take this thing that we already knew and replace it by this new notation. And when I figured it out, I found that in my convention there should have been a minus sign. But this thing is just what we already knew, but now a new notation. There's that. How's the energy levels? Yeah? Alright. Let me now go back to non-inertial frames. Yes?
Just to be sure.
Sure.
When you wrote eta 0 beta, right, that one underlined, in this case we only do the 0, 0 because 0, 0 in the matrix is -1.
Yes.
But normally we should add also, for example, 0, 1
Yes.
in the matrix, etc. In this case it's 0, so it's useless.
Yes.
Okay.
That's it.
Okay.
We're very lucky that our Minkowski matrices happens to come with many zeros. Suppose that none of them were 0. You would have had 16 terms for this double contraction. It just so happens that in the simplest space-time that you have, Minkowski space-time, it just so happens that most of them are 0. Guess what happens in general relativity? Yeah.
Most of them are non-zero.
Yes, so that means that every time you write down something like this, you would have 16 terms. So can you imagine that from that moment on you're very happy with a shorthand notation like this instead of writing down all 16 terms? For here, it is an enormous overkill in notation just to keep track of one minus sign. In general relativity, you're extremely happy that you do this. All right, good. Let's go back to less mathematical notation-wise thingies. Let's go back to non-inertial frames. I'm going to make a statement. I'm going to erase all of this. This is again just notation. This is the thing that we want. Oh, there. From this moment on, I will exclusively write things down in this contraction notation. And only when necessary or things get too obscure, I will write them out longhand again with all the 16 terms. Okay, that requires some practice to be able to operate these contraction thingies. But again, in general relativity, you will be very happy that we've introduced this notation. All right, so this is what we prove now. From now on, the exact same statement that we have used all the way from the beginning is this. Same physics, same mathematics, just different notation. There you go. Claim. Fictitious forces. If you go to a non-inertial frame, you come into fictitious forces territory. And that means that this thing does not hold anymore. My claim is the only thing that changes is the matrix. That's the claim that I'm making. Now before I make plausible that this claim is true, let me say what that means. That means that instead of the matrix with -1, 1, 1, you get these general matrices with all kinds of different numbers and even functions in there. Difficult stuff. But every mathematical trick that we've used to make this invariance and turn this into rules, how things move, the thing that we did last time, time dilation and such, still are exactly the same. It's just that now instead of -1, 1, 1, you have a more complicated matrix. Otherwise, all of the mathematics is going to be exactly the same. But this, of course, hinges on me saying that if you go to a non-inertial frame, the only thing that changes about this whole statement is this thing. I'm looking for a way to get there because I'm sort of giving my lecture in a different order than I originally wanted to. Let's do it like this. If you go to a non-inertial frame, you feel Fichte's forces, but Fichte's forces, according to equivalence principle, are indistinguishable from gravity. Everything moves the same in gravity. Here's the thing. If everything moves the same in gravity, then you should be able to write gravity as a property of space-time itself. Big step. You might have to might want to parse this for a second.
Can you repeat it?
Yes. If things move the same in gravity, or via the equivalence principle, under the influence of a fictitious force, then you should be able to write the motion of things as a curvature of space and time. Oh, well, let's make it plausible
How
here.
did you get space-time?
They want to move in a straight line, but space forces them to.
Exactly. If I want to move in a straight line, suppose I'm a particle and I'm moving through gravity, or if you will, I'm in a non-inertial frame, but we've now seen that this is pretty much the same as far as the mathematics is concerned, okay? That means that I want to move in a straight line, yes? Newton's first law, Newton's first law, Newton's first law. But wait a minute, the path on which I'm walking happens to take a slight turn to the left now. I have no choice but to follow this path. Now suppose that you replace me by any of you, different mass, different hair color, different gender maybe, and you too are walking down this path. You have no choice but to follow this path. Agreed? It's because it's this path that determines where you go. It's the curvature of this path that tells you that you should make a slight turn to the left over here.
So the object will follow the path regardless.
Yes. And the regardless part is the one that we're looking for here, because we saw everything moves in the same way in gravity and or under fictitious forces. So that means that no matter what is walking, all of it should take a left turn here. But that means that you might as well say, well, there's obviously some path in space that tells you where things go, regardless of what the thing is. That statement, that you can translate the fact that people are making a slight turn to the left here, that you can translate that as a statement about the path and not about the person, is exactly because everybody is taking that same turn. Does that make sense? If not, I have another metaphor for you. Let's go with the other metaphor. It's the one that I use when I give a public lecture about these things, and I do that every now and then. And it's the one that I use with trains. I like trains. No, you know what? I should. Okay, I don't have a picture of this one, but there was me in the roller coaster. But in the Efteling amusement park, you also have these rides where you sit in these really old cars. You know these? Have people seen this? No, not bumper cars, because they're fixed on a track. Yeah, and they come on all this bright yellow, red, blue colors, and it's for the smaller children. They sit behind the wheel, and then they pretend that they're steering, but they're not, because the pad they're just attached to a rail, and you go through this park. So I went into that yesterday with my girlfriend, who has a driver's license and I don't, so she thought I should sit there and try this. No, this happened. I mean, I'm not making this up. I don't have a picture of that one, but trust me that I went into that one. The Old Tuffers Club, it's called, I think. Anyway, you're on that thing, in one of these cars, and at some point, the car will take a right turn, because this is the path laid out, the track on the floor that tells the thing that has to go to the right. Now, if I would replace that car, we happen to be in a yellow one, number one, and the one after behind us, I think was a green one or something. Say it was a green one. You put that one in. Different people in there, different color. In fact, you might replace the car by something else that attaches to the track. It will make the exact same turn at the exact same location, doesn't it? Now, the reason is that thing making this exact same turn at the exact same thing is because the turning of that thing has nothing to do with the actual thing. It has to do with the track on which the thing is moving. Now, reverse that argument. Suppose that you find that there are all kinds of things that are making the same turn at the exact same position. You cannot find one exception to that rule. Then, for all practical purposes, it's as if every object apparently is attached to some invisible track that happens to take that turn over there. Do you see that reasoning? Do you see that it only holds if everything moves in the same way? Because if you can find one thing that does not take the turn but takes the other turn or goes in a straight line, then you know, wait a minute, the whole track idea is probably crap, because why can I then find one thing that doesn't follow the track? At the moment that you find that everything follows the exact same trajectory, I shouldn't have done this. Everything follows the exact same trajectory. It's as if there is a track on the floor that tells it where to go. Find one exception and that idea is gone. We are now in a situation where everything follows the exact same track in space. If it's on the gravity or on the fictitious force, it's the same thing. So Einstein said, well, we might as well imagine like there is something in space itself, that tells things where to go. Invisible tracks, if you will. The invisible tracks is what Einstein called curved space. Very simple example. Here's space. Here's a track, or the motion of one thing. Newton's first law tells the thing you should go in a straight line, constant velocity. And then you curve the space. And from the outside it will look as if it has moved. Notice that this will happen regardless of what arrow I would have drawn. This twisting and turning of the arrow of the path is the same for all arrows that I could draw. Why? Because it's not a property of the arrow, it's a property of the space. My piece of paper in this case. Find one arrow that does not do this, and apparently you cannot write it as this invisible track or this piece of paper. So what's the reasoning here? Everything moves in the same way. And then Einstein said it's as if there is a curved space that twists the tracks in space, the invisible tracks, and therefore everything goes in the same direction at the same place.
Oh, is that the famous phrase like space tells matter how to move and
yes.
Matter tells space how to bend?
The first part, the quote that you're using now, for people who don't know it, is the following summary of the whole general relativity. It says, what's the first part?
Space tells mass how to move.
Yes.
And mass tells space how to bend also.
Yes, exactly. Space tells mass how to move. That's this part. Mm-hmm. Once space is curved, masses have no choice but to follow that path. And there's a second part that says that, well, but how my piece of paper is twisted and turned? Well, that itself comes from mass. That's the part we haven't looked at yet. So that's the idea. Is there any conceptual difficulty at this point? If you can find one exception to the equivalence principle, one object that does not follow the exact same path as all other objects also meaning electromagnetic radiation or even gravitational radiation, if you can find one phenomenon that does not follow the same path in space, you cannot make this imaginary step that there's some invisible train track that everything has to follow. Now,
doesn't the track depend on the mass?
Yes.
Just
yeah, that's the second.
Assuming the
that is
objects
true.
are exactly the same, right?
Sorry?
Are you assuming that the objects are exactly the same mass, same
No,
kinetic?
I'm assuming that they're not exactly the same, that it's the same conclusion for all objects.
But if I drive a heavier car on the same road path, it will interact differently.
That's because of all kinds of other influences, like a heavier thing, for instance, will press itself against the road a little bit more, so it gets more normal force and therefore more friction. That sort of things.
So basically you're saying that all objects should have the same laws of kinetics applied to them?
If only under gravity. The whole equivalence principle only holds if there's only gravity, just gravity. So if you take away all other influences, so in your case like friction, say, of the road in the car, then everything will move the same way. Do it like this. You take a little hill and you let a ball move downward. Now, if you take away air friction and you take away the friction between the ball and the hill, the way that the ball will roll down is going to be completely independent of the color of the ball, the mass of the ball, even the shape of the ball. Wait a minute, but the ball should roll, right? Yes, but if there's no friction, then a block will roll just as well. But it will just slide down, both of them will. I mean, rolling only occurs because of friction, but it will just slide down. It will be exactly the same. And again, in this example, very simple. It's because the path of the ball is determined by the hill on which it is rolling. It's not a property of the ball.
But
yes?
But what he was just saying, that in space-time, the curvature of the hill itself comes from the mass of the object.
That is very true.
So then why would all objects have the same path?
Okay, that is an extremely good question. Because what I'm now taking is just the first part of his statement of general relativity. Space tells matter how to move.
Yeah.
Given that space is curved, regardless of where the curvature comes from, everything in that space will have to move in the same way, will have to follow the same invisible track. Now, it is also true, that's the second part, that the way that space-time is curved itself comes due to mass.
Yeah.
So that means, but wait a minute, that means that if you put a different mass there, then the curvature of space will be somewhat different still. And there will be some difference. So let's make it more specific. Suppose that I have a curved space-time and the curvature comes from some external mass. And we're going to add to that a smaller mass that is small enough not to disturb the curvature of space-time, even though it does by a small amount, but yet big enough to follow that curve. Then it will be the same. This is called a test mass, by the way. Now, if you think, wait a minute, but this is sort of cheating, but how can you, I mean, you're going to add a mass, so it will follow the same path, but the mass is not allowed to be massive enough to itself curve space. This is what we do in gravity all the time now. Because even if you didn't, when you did Newtonian mechanics, when you do an exercise where you drop a ball on the floor, just Newtonian high school mechanics, in principle, what you should also calculate is how much the Earth itself is moving upward while you're dropping the ball. Nobody ever takes that into account, right? The reason is because we assume gravity to be so big due to the Earth that the little bit of extra gravity that you add because of the smaller ball is completely negligible. That's called a test mass, and it's not entirely correct. Now, we're going to assume that the background space-time is ridiculously curved due to some other external influence, and that the thing that we're looking at is moving on that curved space-time itself is not massive enough to disturb that. The effect does exist, and it's called the gravitational self force. And it's a ridiculously difficult problem in general relativity to solve. But fortunately, you almost never have to solve this thing, because if something moves around the black hole, say, well, you can safely assume that the black hole is too massive for that little small extra thingy to make any difference.
Sorry,
yes?
You said that this law should only apply if only gravity is there.
Yes.
So we allow magnetic fields to deflect objects.
Yes, then things will move different, of course. If you add some gravity, some magnetics, say, then of course things will move differently. Yes. So all of this only holds at the moment that there's just gravity and gravity alone. We've now reduced gravity as a force by gravity as a hidden track in space. So the only thing that we have to do is find out what the hidden tracks look like in space, given a certain amount of external mass twisting and turning the space. Now, if you go back to this expression, this thing tells you where things are, yes? It's how much a particle has moved from one moment to the next, from one position to the next. Remember that these are 4 numbers. The amount of change in time, and 3 times the amount of change in space. dt, dx, dy, dz. So this is really, this one, and also the other one, is really just a measure of how much things has moved. In a certain amount of dt, how much has dx moved. So this tells you the motion of things. This tells you the curvature of space. Now, if we've now seen from this hidden train track metaphor that all things move the same in a curved space-time, and that difference in motion is only due to the curvature of space-time, and we know that this is a measure of the space-time because this is, a measure of the motion, so this is a measure of the space-time, then I hope that you see that the only thing that changes when you add curvature or gravity is this number. Again, a big step here. These two are measures of motion, how things move. This thing is a measure of the curvature of space, what space-time looks like, where the trajectories are, the hidden tracks. If you know that by the equivalence principle everything moves, or let me rephrase, that gravity translates itself into a curvature of space-time, then it must be encapsulated here in this thing. That's the conceptual step. Let me write it down. This thing measure of curved space-time. So therefore it is here where you find your effects of gravity and or your fictitious forces. Those are the huge steps that we made today. We started by saying that gravity is Newtonian physics. Then we saw that, wait a minute, it behaves the same as a fictitious force in a non-inertial frame. Then we saw, wait a minute, but if things move the same in a curved space-time, under gravity, then therefore you should be able to write it as a curvature of space-time. And since this is a curvature of space-time, this is the part where you should see your fictitious forces and or your gravity. That's the series of steps that we made. The only thing we have to do now is two things. One thing is, okay, if somebody gives you what this matrix is in a curved space-time, and it will not be -1, 1, 1, 1 again, but some more difficult object, how then can you calculate how things move? I've just told you this thing contains your hidden train tracks. It does. I still have to tell you how to get the train tracks out. It is hidden in here, but you have to pry it out. How do you do that? That's one step. Second step is, where does this curvature itself come from? What dictates what these numbers in this new matrix are going to be? Now both these things I'll explain to you next week. We have done some enormous amounts of steps here, so you might have to parse this. Let me give you the general relativistic version of this statement. The statement is exactly the same. The only thing that you have to change to go to curved space-time or go to a non-inertial frame is replace this matrix by the new matrix. This new matrix people call G mu nu. Oh, we promised to call it alpha beta. Although, again, relativists always call it G mu nu, but that's called alpha beta. Everything is exactly the same, including the statement that this is invariant. It's still invariant. The only thing that has changed to account for the fictitious forces and or your gravity is the numbers in the matrix. This thing is called the metric tensor. That's what it's called. Again, two things we have to do starting next week, and that is I'm going to give you a number of these metric tensors for specific cases, and then we're going to use our invariance and all these tricks that we've seen last week to see how things will move in that curved space-time. We're going to pry out the hidden train tracks. Second, I will have to tell you where these numbers come from in the first place. Or to put it in his terms, next week I'm first going to tell you, given a metric tensor, so given a curved space, how things move. And then I'm also going to tell you, if you have masses, where does this come from? Matter tells space how to curve. So there's two things we still have to do. But this is the mathematical structure. Yes, you had a question.
So, if the thing on the left is invariant, why does that automatically make the thing on the right invariant?
That is a very good question. Let's see if somebody knows the answer. This one we took as a postulate, yes? It was our starting point. We just said, well, suppose that it is. See if we can find something that agrees with what we measure. Can anyone give me a statement that if I replace the Minkowski metric by a general metric, I still keep my invariance?
You still have C squared and tau squared.
Yes, but okay. Yeah, but then the question is this d tau squared the same as that d tau squared?
The Minkowski matrix would just be a unity matrix, right?
With an additional minus sign in one term.
Yeah.
Right, it's minus 1, 1, 1.
Then
Minus 1, plus 1, plus 1, plus 1.
But then this won't change anything about the dimension of the problem, right? It will just
That is true.
rescale everything.
That is true. We're not quite there yet, but maybe you can make this step. It's a very extremely good question. Why can I assume that that thing is invariant as well? Yes?
The metrics with eta, right?
Yes.
This one is the specific one with we saw before, right?
Yes.
And for all the matrices, we just use G.
Yes. That's the idea, yes. Question still stands. If I know that this one is invariant because it's our postulate and everything that we derive from this is something you can just measure and you find that it agrees with experiment, why can I say that this is invariant as well?
Why are these two expressions different? Is by definition the G and the eta different matrices?
Yes. One of them is, this one is if you are in inertial frames, and this one is if you're not in inertial frames.
Is it important to know what the contents of that matrix are right now?
No, I will give you some starting next week. In fact, the last 3 weeks, next week I'm going to tell you how to pry out how things move. And then the last 3 weeks, we're going to apply this for black holes, the universe itself as a whole, and gravitation waves. So we have 3 lectures where we're actually going to apply this statement and see what happens. But it is going to be important to find why is this invariant. Otherwise, all of it will have no meaning.
If you don't know the contents of the matrix, how can you prove anything mathematically?
Well, maybe you don't have to prove mathematically. Maybe there's a physical reason why this is the same. Yes?
For next week, how much knowledge in matrices do we have to follow?
Almost none. Okay. If the one that I gave you, I take it you haven't done linear algebra.
Yeah.
Okay. The only thing that you have to remember is this notation that if you see this double alpha and double beta, that you know how to write this out.
Okay.
Which is, for the people in the know, it's a kind of matrix multiplication. People in linear algebra never wrote it that way, but it is. If you're not seeing that, don't worry about it. If you know this notation, you should be fine. It does help if you know some linear algebra. Forget about it for now.
I'm going to read a bit about it. But
Okay. Just fix on the definition of this Einstein summation convention, and you should be able to manipulate these things without knowing linear algebra. It's nice if you know some, because then you can easily see the connection between what you've seen there and this. If not, you should still be able to do the calculations. Question stands. Yes?
Maybe if you have 2 objects and you treat them as one big mass and they make a curvature in space-time, their constituent curvatures should add together should give you the overall curvature. No? Because you say you want the physics reason.
Yeah. No, I'm parsing your idea. You might be right. Let me parse it a little bit more. I think there's something in there.
Small magnet.
No. What he said was, well, suppose that you have some external curvature, the one that makes this thing turn into that thing. Okay? And you want to know how another object moves in that other curved space-time of the bigger object. What if you see them both as this one big object? Isn't that the same thing as saying you have this one big object, and because there's nothing external curving space anymore, because you've made it one big object, you should get back to this one or something like that. I mean, there's something there.
I'm not even sure how this proves that that's invariant, but I suspect that it shows a symmetry to the system that's conserved.
I actually like that argument. I have to parse it. My first feeling is I think it's at least half correct. Or maybe it's 100% correct, but as far as I can tell, there is definitely something in there. Hey, what kind of frames are you allowed to move to if you go from one frame to the next? In general relativity. Are you restricted by inertial frames?
No.
No, you can go to any frame that you want, right?
Yeah.
So, but doesn't that mean that you can turn this thing into just that thing, by just going to the appropriate non-inertial frame?
Guess so, yeah.
If you go to a
Yes.
non-inertial, we introduce fictitious forces. By
Yes.
introducing fictitious forces, this thing turns into that thing. Remember? That's the whole basic, that's the whole structure of argument here. So how about if you can turn this thing into that thing just by going to a non-inertial frame? This thing just carries over.
Right. Yep.
Yeah.
That's the whole idea here. You are now allowed to go to non-inertial frames. Non-inertial frames gives you the effect of gravity. The effect of gravity turns this thing into that thing via curved space. If you're allowed to now to go to non-inertial frames, that means you're allowed to change this thing into that thing just by going to a non-inertial frame. You see somebody throwing strobe up and down, he's in an inertial frame. Accelerate with respect to that guy. This thing will turn into that thing, and the invariant part just carries over. Yes?
The last formula, can you use this also for inertial frames, or is it not?
Yes, you can also use this for inertial frames.
So this is like the whole
This is
general
a
formula for everything.
Yes, and now you understand why general is in the name of the of the topic. I mean, this one holds exclusively for inertial frames. This one holds for all frames, including inertial frames. And if you go to the math, you will find that for inertial frames, this one automatically reduces back to this one. So this is the general one. This is the one that we're going to deal with from now on. There you go. And again, we know. Yes, please.
Can you quickly repeat the reasoning? I didn't follow.
Okay, so can somebody else repeat the reasoning just to see if things got parsed
I
correctly?
think if you just think back to those fictitious forces we had before, we talked about how if you are actually moving in a non-inertial frame, you'll see these fictitious forces, and you can make them go away or something by viewing it from another reference frame, right? From
Yes.
from an inertial one.
Non-inertial.
Non-inertial.
Okay.
Okay.
It would have to be.
Yeah,
You
yeah.
see them as standstill.
And it's difficult to work with, like somehow the same applies to this, right?
Yes.
Yeah.
In essence, you're correct, though. I mean, maybe the phrase you can use work, but then again,
Yes, of course.
it's different. It's not a statement about you. It's a statement about the subtlety of this argument.
Yes.
You can be at rest within a non-inertial frame, right? If you're in a non-inertial frame yourself.
Yes.
So that proves that you can observe the same invariance in an inertial and non-inertial frame.
Yes, exactly. Because you are free in general relativity to move in and out of inertial frames, and you know that in inertial frames holds this, but you're allowed to go to a non-inertial frame, and the non-inertial frame will give you fictitious forces. Fictitious forces will turn this thing into that thing, but because you're allowed to do so, the invariance just carries over.
So it's used by the definition of general relativity.
Yes, but it's not a semantic argument. I mean, I explicitly use the equivalence principle here. Right? The equivalence principle is at the heart of us being allowed to use a curved space-time to write the effects of gravity. So it's not just semantics, not just, well, I just define this as general and therefore such and such. No. It's such an important point that I feel like I should say this again. The fact that the equivalence principle holds, that is that thing that allowed us to write all of gravity effects as a curvature of space-time, right? You see that point it should be really clear. I mean, feel free to think about it for a little bit over the next couple of days, but that, at some point that point should be clear. The fact that the equivalence principle tells you that things should move the same in gravity, that allows you to write motion in space-time as a result of curvature. And it's because of the result of curvature that this thing is the thing that carries all your information about gravity, or if you will, fictitious forces, or if you will, non-inertial frameness. So, having established that, knowing that you're free to go to any non-inertial frame, and knowing that because of the equivalence principle, all of that information can only be in here, this is what allows you to write this as such by making the right transformation to a non-inertial frame. So it's not just semantics.
Well, like, that makes sense to me, but that
Okay.
doesn't say that it's invariant, still, to me, at least.
I'm not sure why not.
Me neither. It's just like the invariance, like we always proved it with like having something in the prime, non-prime, and then
Yes.
the math adds up, and in the end it's equal. But I don't see it there. Kind of.
Well, this is why I call this a physical a line of reasoning.
Yeah.
To be honest, I'm not sure what to add to it in what way I can rephrase this. I'm trying to explain this by metaphor, by looking at something else in physics where you apply the same trick. Let me think about it for a while. Maybe I could think of an example that looks somewhat similar, where it's somewhat easier to see.
Okay.
Let me think about it for a while. I might come back to you.
Maybe I just need to like think it through a lot.
Well, there's a lot of conceptual new steps here. I mean, that I fully agree. Now, if you want to read about this, this is exactly what chapter 6 tells you of the book. I very much urge you to read through this because the exact same style of reasoning is in here. There's almost no mathematics. They do use some mathematics because they introduce a particular choice for this general metric and do some calculation with that. You can skip that part. The rest of the chapter 6 is just talking about why this style of reasoning holds. So maybe that's the best advice for people who are not parsing this immediately.
Yeah.
Chapter 6 will tell you the exact same argument, maybe in somewhat different terms. This is it though. And this is all that I wanted to say for today.